For our last video in 5.2 here, we're going to continue looking at Riemann sums and go into a bit more detail here. So from the last video, remember the Riemann sum is the sigma notation form for adding up the area of a lot of little rectangles so that we can find the area underneath the curve. And so we drew out our rectangles there and we looked at the area of a sample rectangle, the kth rectangle out of all of these. So first rectangle, second rectangle, kth rectangle. And we ended up finding the area of that kth sample rectangle. It was f of ck times delta x sub k, where ck are the different points that you can use to set the height of your rectangles. Remember from 5.1, those are your different types of endpoints or your midpoint. And delta x sub k is the width of each rectangle. That's the distance traveled along the x direction there. So the Riemann sum is adding up n of those little rectangles to approximate the area underneath the curve. All right, we go from rectangle number 1 to rectangle number n. And then for each rectangle, we put in the area formula for that particular little rectangle. All right, so we're just taking this and putting it right into our Riemann sum. Now we want to look at some more detail on those different pieces of the area formula, because there are kind of some default settings that we work with for these Riemann sums in general. And the first one of those deals with the delta x term. So when dividing the x-axis from x equals a to x equals b into n equal length subintervals, we can use a certain formula here. And the key words here are really n equal length subintervals. That means n rectangles, and they're all the same size as far as their width goes. So I'll make a little note of that. All the same width for the rectangle. Okay, because remember, when you're making your partition of this interval from A to B, you actually don't have to use the same size of rectangle for each individual rectangle in there. In some applications, you can choose to use larger rectangles and smaller rectangles in different parts of the curve, but that is a more complicated process that we actually don't cover in Calc 1. So you'll have to go on to higher maths to get that part. We're going to work with n rectangles that are all the same width. All right. So if we're taking that interval that we're looking at from x equals a to b, and we're cutting it up into n equal pieces, we're just going to take that length between the two. This would be b minus a for the length of that interval. And we're going to chop that into n equal pieces. So that's the formula that we can use, is delta x equals b minus a over n. And you can call that, delta x is just making it nice and generic there. This is a replacement for delta x sub k, because if all the rectangles are the same, we don't really need to denote whether it's the first, second, third, kth rectangle. They're all just the same delta x. So we can kind of ditch that little k and just say, okay, delta x is b minus a over n. All right. Now, remember from section 5.1, if you want to make your area estimate more accurate, you can use more rectangles. All right, increase the value of n, because n is your number of rectangles here. That's going to make the rectangles thinner, all right, because you're increasing this denominator value here while still keeping b minus a the same interval. So that's going to make the rectangles thinner and make our area estimate more accurate. Okay, so keep that idea in mind, increasing the value of n. Keep that in mind for the next section. Okay. Now for our CK points. Remember, those are what we're using to set the height of the rectangle. And those selected points have different options, right endpoint, left endpoint, midpoint. And for our default Riemann sum, the default that is generally used are the right endpoints. Now, there may or may not be a great reason behind this. It's just historically what has been accepted as default setting. Okay, so we're going to find a formula for locating the right endpoint of each little rectangle because we're going to need that. So let's draw a picture here. You know, I love my pictures. If we start from one side of our interval, start at x equals a. Okay, we're going to have something like this. Okay, there's x equals a. And then I'll just say this is where our first rectangle would end. All right, so the rectangles are sticking up from this little x-axis here. Okay, they just go up. All right, here is our first right endpoint because that's the right side of this first rectangle. So, whoa, I dropped my pen for a second there. But that's our first right endpoint. This is C1 because this kth rectangle, this is the first rectangle. So this is C1. And then this right here would be C2 for the second rectangle. All right, that's the right endpoint. And then C3. And then you would just keep going on and on and on until you got all of your rectangles accounted for. Okay, so this goes on. Now, remember that each one of those rectangles, we just set the default width as being delta x, not delta x sub k anymore. We're saying they're all the same width. Delta x equals b minus a over n. So let's keep it simple and just label each one of these widths with delta x. Delta x, delta x, and that pattern would keep repeating. If you want to draw a couple more rectangles, no problem. So let's come up with the formula for these first couple of right endpoints. All right, on our first rectangle, we're getting the point C1. And we could find this x value right here by starting from x equals a and then going over this much distance, delta x. That would take us to the point C1, right? So the x coordinate for C1 is just going to be a plus delta x. That'll get us there. All right. Now, if we go to our second rectangle, we're going to do that same type of thing to find the right endpoint C2 right here. Okay. Now you could say we start from C1 and move over another delta x units, but let's keep our formula consistent here and start everything from x equals a. Okay, so if you start from x equals a, to get to C2, you're going to have to move over delta x units and then another delta x units, and that'll bring you to the x coordinate for C2. So that would be a plus 2 of these delta x distances. All right. So far, so good, hopefully. Let's do one more here just so you guys can really spot the pattern. Let's check out our third rectangle. Okay, that right endpoint would be C3 right here. And if you can spot the pattern, go ahead and write the formula down right now for C3. See if you can get it. Okay, and now you can double check. Okay, if you're starting from x equals a, like we have been, to get to C3, you need to move over delta x units, and another delta x units. And that'll bring you right here to C3. So that would be a plus 3 delta x. All right. So what do you think C4 would be? If you look at our pattern here, C4 should be a plus 4 delta x. All right. You take whatever rectangle you're on, and you need that many delta x's. So if we make this generic for the kth rectangle, we can find the right endpoint, ck, by taking a and adding k of those delta x terms. A plus k delta x. All right, it's just following that same pattern. First rectangle has 1 delta x, second 2 delta x, third 3 delta x, kth k delta x. So follows along there. So when we put all of this together for our Riemann sum formula, remember our original looked like this. S of p equals the summation from k equals 1 to n of f of ck delta x sub k. Okay. The default is going to incorporate what we've just looked at. You have n equal rectangles. And you also have right endpoints for your defaults. So that would make our Riemann sum look like this. The Riemann sum for these n equal rectangles is going to be the summation from k equals 1 to n, f of ck, but we have a formula for that now, so we're going to put that in. So f of a plus k delta x, and then times delta x, because we've eliminated that little delta x sub k since they're all the same size. And then you could also put in that delta x formula that we had. S sub n equals summation k equals 1 to n f of a plus k times delta x. And our delta x formula was right up here, b minus a over n. So k times b minus a over n, and then all of that times another delta x, b minus a over n. Okay, so you can memorize it in this form if you would like. The way I'm going to break down Riemann sums for us, I actually tend to use more of the original Riemann sum type of setup, but it all comes back to these same ideas. Okay, so these are good formulas to know. Your delta x being b minus a over n, your ck's, those right endpoints, being a plus k delta x. So those are things that are going to come up in the next section. And so that's good to know where these are coming from.